Okay, hi everyone. I'm Daniel Eriksson, and I will talk a little bit about automated bucket filling for wheel loaders and how to use AI and machine learning to solve this task. I am ESR number 6, and I'm a PhD student with Tampere University, but I spend most of my time at Liber in Austria. So, firstly, a little bit about the agenda. So I will go through the process, the task at hand. And then, a little bit, what are the options? How can we solve this problem? And then the research questions that I had, and the concepts, and also the experiments and the solutions that I've come up with. So first, we'll start with the bucket filling process. So the bucket filling process is what you can see here in the video. So this is a human operator operating the machine, loading some kind of sand material. So this is the bucket filling task, and usually a wheel loader, you take a bucket with material and then offload it somewhere else. But during this working cycle, the bucket filling task is the most challenging part, so to say, because it's where you need the most skill from the operator. It's also where you use the most fuel from the machine, and it's also where you can do most damage to the machine. And it's also, as you can see, like driving around with the wheel loader is quite easy to do. Like it's driving a car. Everyone who has a driver's license can do it, but filling the bucket is more complicated and challenging. You need more practice to do that well. And if you don't do it well, it will affect the cycle in many ways and affect the machine in many ways. And for the bucket filling task, we have 3 degrees of freedom. So you can lift the boom, you can tilt the bucket, and then you can use the throttle to go into the pile further. I also have a different example of a bucket filling. So this is also a human person loading. Here is some kind of stone or like blasted material, which is much more, bigger rocks and so on. And here you can see that he really needs to use some different techniques. He needs to be more aggressive to get deeper into the pile and so on. So therefore I come to how we can solve this. So we can have like a classic engineering approach, or we can use some kind of supervised learning or reinforcement learning as well. But for the first, like classical engineering approach, is one example is that you can look at some kind of data from a cycle, and then you can try and derive some rules from that data. And then you find some conditions and build a state machine around it. And then try to replicate the behavior of the human by hand. And this requires a lot of knowledge and so on. So you can summarize this with that you have some kind of input, your data, your variables, your forces and angles, and then you define some rules, and then you will get what the operator is doing. And here is one example. So here we have, okay, so, we're back. So here we have one bucket filling. So here it is, he's going to the pile, here he's digging through the pile, and here he's leaving the pile. And here we have the angles of the boom in the bucket, we have the forces in the lift and tilt cylinder, and we have also what the operator is doing. So it's not really straightforward. How do we convert these 2 upper graphs to this 3rd graph here by some logic and some rules? So one example of like a state machine could be that you lower the bucket to the ground, you drive into the pile, you lift a few centimeters, you increase the throttle, and when the pressure is 210 bar, you start lifting with 17%, and so on and so on. And it gets quite complicated quite fast, and it's quite, it's not really easy to find a robust way to deal with all sorts of different kinds of materials with this approach. So here is one example of this rule-based bucket filling system. So this is an assistance system that we tested. And as you can see, it's not really working that great. It's only not even getting a half a full bucket. So this is like what you can get on the market at the moment. But then, so this first approach has some robustness issues. So what can we do instead? Yes, so we can either use supervised learning. So we have a lot of data, and we take this data and we train a model for it, and then we get the outputs from the model. So this can replicate what the human is doing, but it also requires a lot of labeled training data. So we need to collect a lot of data from the machines for different materials and different operators. So here it's a little bit the other way around. Instead of having input and some rules, we get the output. Here we have the input, so the angles and forces. We have the output, what the operator is doing, the command from the joystick and throttle pedals, and then we create some rules from that. And then the third option is we can use reinforcement learning. So here it learns by itself, and then it optimizes the digging behavior after each bucket filling. And here we don't need any labeled training data. We don't need any training data collected from a human operator. But we instead need to define a reward function, which can be quite challenging and tricky to get it correct, so that the machine is doing what we want it to do. And then, this has the potential of being even better than the human. So that is why this is a very interesting approach to do. And then here I have some examples of some supervised learning and some reinforcement learning. So here, the first image on the left side, we have some object detection. So this is some heavy-duty machinery. So here they use supervised learning to classify these different machines. We have some wheel loaders and trucks and so on. Here on the right, we have this robot arm learning to pick some of these plastic things from a bin. And in the beginning, it's just doing random motions. But then it's trying, and you define a reward function when it's doing good. And then after a while, it will learn to pick these bins or these plastic things quite efficiently. So then we come to the research questions. So the first research question is that, like, which AI models are appropriate, or network architecture. So, I mean, there's a lot of things that you can try, but these are the ones that I chose to try based on previous work and also what's feasible to do. So we have, the first fully connected layer, a simple model, and we can have some convolutional neural network. We can also have some long short-term memory, and we can also have like a random forest. So then, this was the first question to test what is working, which models are working well on this problem. And then the second question, how does quantity and composition of training data affect the digging performance? So this is basically how much training data do we need, because it's quite costly to gather all this training data and record it. So it's interesting to know how much do we actually need, and if we scale this up, how good performance can we get if we collect more and more data. And then the third question is about material transfer. So how can we share knowledge between the materials efficiently? Because, I mean, as you saw there, you have to load the materials a little bit differently, but they're also quite similar. So there's a lot of things in common. So you can probably share some of the knowledge that you use from one material to another material. And then lastly, the last question is about reinforcement learning. So how can we use reinforcement learning to self-optimize in the field to some unknown material that we haven't seen in the training data? But first, I will show a little bit of the training data that we collected. So here is one example from a recorded time series. So we recorded when the operator is doing a lot of different tasks. And then here we have recorded like the pressures and the angle of the boom and the bucket, and also the speed of the vehicle down here. So he's doing a lot of different stuff, but we only care about these parts that are highlighted in yellow. So these are the actual bucket fillings, and whatever he's doing in between is something else that we don't care about for the training data. So so in order to do this supervised learning, we first had to collect the data, then extract these bucket fillings. But when we have the bucket fillings, we can rank them according to some metric. And then we can sort them, and then we can discard the ones that are bad. Because when we used supervised learning methods, we want to have only the good data. So if we have bad data going into our data sets, our model will not perform as well. So we want to just get rid of all the bad data before we start training. And then, so how do we actually solve this problem in reality? So then we developed this bucket filling algorithm. So the bucket filling algorithm can be quite roughly defined into 3 phases. So here we have the approach phase, and then we have which is, it's basically where you go to the pile, and then you have the digging pile or loading phase, and this is where you actually fill the bucket with material, and then you have the last phase where it's the exit, which is the exit phase. So we made a simple state machine that in the beginning it would just go forward automatically with 50% throttle so that it would end up in the pile, and then when it reaches a certain force threshold, we will activate the neural network, and then it will do the digging. So the neural network would then has 5 inputs, and it would take the tilt angle, the lift angle, and also the tilt pressure, or the tilt force and the lift force, and also the speed of the vehicle. And then it would output 3 commands. So this would be the same as operator commands. So you would have the tilt of the bucket and lift of the bucket, and also the throttle of the machine. So that would be the gas pedal and joysticks, basically. And then after it's finished, we will just, make sure that everything is tilted in, and then we can weigh the bucket, in order to see how much material we got. So, and then here are some of the results that I got. So first, for the first question, how the different models would perform. So here we evaluated on this gravel pile that we used. So, and this gravel pile was also used for data collection for this experiment. So yes, here we can see the different models on this graph, and the blue thing, the blue bar is how much material was in the bucket, and of course more material is better. And then the orange one is the loading time, so how fast the model was at loading the bucket, and of course it's faster. It's better if it's faster, so that means a lower is better. We also have the human performance, how the human was doing. So that is the horizontal line. And then the mean of the human is in the dashed line, and the thickness of this horizontal line is the variance. And as you can see from this experiment, that the CNN model that we created worked the best. It could get more than the human on average, and it was a little bit slower, but still within what the human was loading. And then for the second experiment, we tried to answer the third research question. So how can we combine the training data? So here we collected data from 3 different materials. So we have sand, then we have some kind of gravel, and we have some kind of blasted rock, but with smaller rocks. And then we used the best model from the previous experiment to this experiment. Yes, and here we collect, like I said, we collected about 100 bucket fillings from each material, and then we combine it in different ways. So you can either, combine all of the training data, you can take a little bit from every pile, or you can take everything from one pile and only a few samples from the other pile. And here we could see that it was really best to train on the complex material, so the blasted rock, which is a more non-homogeneous, and you have different kind of sizes of the rock. And then you can use, if you want to have the best performance, let's say on the gravel pile, you can take the blasted rock pile and only a few of the bucket fillings from the gravel pile to get really good performance on the gravel pile, which is what you can see on this graph. So this is the best one that we had here. It got more material than the operator, and it also was much faster, or it was not much faster, but it was about the same speed as the operator. And then for the second experiment, or the third experiment, but the second research question, how much training data is necessary? So here we collected another kind of material, and it was also blasted rock, but this time it was much bigger rocks, as you can see on this image here. And this is quite a complex material, so it's quite hard for the human to load this as well. So you really need an experienced operator to load this efficiently. And here we collected about 2,000 bucket fillings from this pile, and then we made different data sets with different sizes. So we made data sets with size 10, 20, 50, 100, 500, 2,000. And what we can see from this experiment is that, all of the bucket fillings that we tested could complete the bucket filling successfully, so it didn't get stalled or it didn't get stuck in the pile anytime. And so even using only 10 bucket fillings, we could get like quite good performance. We could get, I mean, not as much as the human operator, and it was slower, but still quite good. And then we also added this productivity bar plot, which is the green one. And here you can see a clear trend. When you have more data, you, as expected, you increase the performance. But what is interesting is that, like, even after 100 bucket fillings, we have like similar performance in the material weight as a human, not as much. But then when we use more data, we only get faster. We don't get any more material in the bucket. And then we will come to the reinforcement learning part. So reinforcement learning in the real world is quite challenging. So learning from scratch on the machine is not really feasible in our case, because it will take quite long to do this, to learn it from scratch, and it will have some random behavior in the beginning. So what we will do instead is that we use one of the models earlier that I showed you as a pre-training example, and then when we have pre-trained on one material, we can use reinforcement learning to optimize on a certain pile or maybe on an unknown material that we haven't even seen in the training data. So this is some videos from the experiment. So here we have, this is the pre-trained version of the bucket filling. So here it's pre-trained on blasted rock, and here you can see that the pre-trained version was already better than human. But then, as we did here, 20 bucket fillings, so 20 episodes of reinforcement learning, and then we could increase the material with about 700 or so kilograms, and then we could increase the bucket filling speed with 0.6 seconds. So, and then we have the next video. Here is where the optimized version is. So, I mean, they looked very similar because the bucket filling was already quite good in the beginning, but it gets more material and is a little bit faster. Then we also did another experiment, which was to see if we could use a very different material and still get good bucket filling performance. So here in this video is trained on this wood chip material, and you can see it's very bad. Like, it doesn't even get half a bucket, and it's quite slow as well. But this is expected because wood chip is quite different than the gravel material that we're trying to load. But we can see from the graph here that after 50 episodes, we increased the weight to human level performance, and the timing is also a little bit faster. So as we start training, the weight and the time increases, but then after around 30 episodes, the timing or the loading time starts to go down as well. So here we have the optimized policy after 50 episodes. So so then we have some conclusions. So yes, some overall conclusions from everything is that AI-based bucket filling is working. We can have performance that is like on par with the human, and sometimes we can even be faster than the humans. And it can also load quite well this blasted rock with the really big rocks quite well, even though it wasn't as fast as the human or as much material as human. And then finally, we can also use RL to out-opt the network to different materials. So yeah, that's all. Thank you.
And we can have a quick question before we move to the next one.
So what did you use as observation?
Mm-hmm. We used here. So we use on the left here the bucket angle, the boom angle, and then the force in the lift in the tilt cylinder, force in the lift cylinder, and the speed of the vehicle.
Very good. Okay, so the things that come from the environment are basically two different forces.
Yeah. Yes. So we have on the machine we have angle sensors to measure the boom and the bucket angle, and then in their pressure sensor in the cylinders, and then from the pressures we can calculate the forces. For this we use the proximal policy optimization. Yeah.